Okay, so today is Thursday, November the 12th. This is advanced level chemistry here at Spain Park. Welcome to those of you around the world watching this exciting video. All right. Yesterday or Tuesday we went through and we did the flame test. You just turned it in, okay? Why do things, well, first off, how is all light produced?
By electrons moving.
Electrons moving from where to where?
Different feed, like the rings they go out.
From one energy level to another. Now, do we see anything when the electron goes up?
No.
But it naturally comes back down is when we see. How do we make the electron go up to the excited state?
Heat it.
You heat it or
Electricity.
add electricity. Those are the only two ways in which light can be produced. That promotes the electron up and then comes back down. Okay, so that's kind of, now why do different elements have different colors?
They all have specific,
develop certain frequencies.
Okay, and each color is a certain frequency, but why does an electron in, say, I think we said scandium 3 to 2 be different than a hydrogen 3 to 2?
they go down. Number of protons.
Okay, it's the number of protons. Every element has its unique set of protons, therefore the energy level is going to be different for each one. But it's still the same model for everything that we do. It's just the energy differences between the first, second, third, fourth, fifth, sixth, seventh energy level. Okay? Then at the very end of class on Monday, Clay and I were up here demonstrating a standing wave. What is a standing wave? What did it look like?
The trough stays in the same spot.
Okay, it's just, instead of seeing it move back and forth, it appears that it's just going up and down. But the reality is the energy still transferring, it's just you're getting constructive, destructive interference. You're getting a wave characteristic. Okay, putting that with Einstein's explanation of light being dual nature, combine that with Louis de Broglie's matter waves, Erwin Schrödinger then went and explained the energy of light, the energy of the electron, I should say, in the exact same way Bohr did, but treating the electron like a wave instead of a particle. Okay? The electron is crazy. How can it be a wave? How can it be a particle? And the reality is that we can't observe it as both at the same time. There's a famous thought experiment. Now, this experiment was never done, okay, so no one get upset about this or anything. But you put a cat into a box, okay?
I like where
In the box is a vial of poison. The poison is connected to a switch which is activated by radioactive decay. So you have a radioactive particle that has a 50% chance of decaying. All right? Now, if it decays, it breaks the vial, poison's released, cat dies. If it doesn't decay, vial doesn't get broken, the cat lives. According to Schrödinger, the cat is both alive and dead at the same time until you observe it and force it into one of the other states. Okay? Until you observe it to force it. So you open the box, either the cat's alive or the cat's dead. But until you observe it, it can be both alive and dead at the same time. That's the way we look at the electron as far as being a wave or a particle. It's both at the same time until you go to observe it. When you go to observe it, then all of a sudden, it changes. It's going to be one or the other. You can't observe both characteristics at once. Now I'm just going to show you a little video clip. Does that come on? Did we hear beep? Yeah.
I don't like my cat. I'll volunteer.
Dang.
It's at my house.
Do you want my dog?
I have a little yuppie. I've got a cat in a box.
Do you want my dog?
What's wrong with it?
Nothing. No.
My dog has
Dog.
Christmas pajamas.
Why would you hate my dog? He's adorable. I mean, it's like,
Christmas pajamas. Well, my sister ordered us matching, and then there was this dog one, so she got that too. But literally when we put it on her, she does not like it. What?
My mom said my cat dies really
All I heard
fast.
was my sister pajamas, and I was like,
It's my cat that
Is my sister what?
is your sister college?
Yeah.
And you don't have matching pajamas?
Well, she's coming home. Like after Thanksgiving, she stays home until January. But she's like, she went on Target and was like, oh my gosh, we should do this like last year. But anyway, so Lola has pajamas too, and we put them on her. We put them on her, and the back legs are like too big.
My dog has pajamas. It's embarrassing.
Mine's just, we got mine Christmas pajamas, and that's ours. Anyway, she looked really cute, and then she like tried to get it off as soon as we put it on. It was really funny. She's like,
Radiating out,
Just restart it.
striking the back
I feel
wall
like it should be
with
considered
the most
animal abuse,
intensity
like
directly
make animals
in line with the slit. The line of
We're gonna
brightness
start
on the
this
back
over.
screen.
Go ahead and make it full screen as well, please. Okay, so this is just a crazy example of the weirdness of the electron.
And here we are, granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The
Rectilinear
line of
propagation.
brightness on the back screen shows that intensity.
If you follow the
This is
point
similar to the
all the way
line
through,
the marbles make. But
it's called diffraction.
when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now, there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is matter, through two slits, we get this. Two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. We get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, netherworld of quantum events. What is matter? Particles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
All right. What did you guys take away from that?
That it can change.
It does whatever it wants.
Well, that the electron is both a wave and a particle, okay? But we can't see it as both. What's interesting too is that they've done other experiments to where when they were showing observing before it went through the slit, but you can also observe it after the electron goes through the double slit, and it's still, if you observe it even after it goes through, acts like a particle. You don't observe it, it acts like a wave. It's crazy. Nobody can really understand how that can happen. How can observing something? So there's all kinds of philosophical debates on whether or not your consciousness can affect matter. Okay, just what point of observing is it? Is just the fact of light being shown on it? Is it the fact of it where it's not until it hits your brain? You know, it just gets into a very deep, weird world. Okay? But what we're going to take away from this is that that electron can act like a wave or a particle. It's a wavicle. Schrodinger described the energy of the electron based on its wave, that it's in a standing wave pattern. And in Schrodinger's very complex equations, he has 4 variables which are called quantum numbers. Variables in Schrodinger's wave equation which limit and describe the energy and location of an electron. All right. 4 variables. The first one is the principal quantum number. Here we go, capital P. When you spell it principal, what does that mean? Main. Okay? Mr. G is the main guy. He's the head guy. He's the number 1 guy. Okay? Principal in this case. This is the main quantum number. This states the energy level the electron is on. And E minus is an electron. okay? It can only equal 1 to 7. Now, if you recall, when Clay and I were doing the standing wave pattern, there were only certain energies, certain wavelengths that would make the standing wave pattern. If I didn't have the energy just right, it was just kind of chaos. Schrodinger said the same thing. There's only certain places, certain distances from the nucleus that the electron can have these standing wave patterns. So he was able to have the whole idea of energy levels, distances from the nucleus, based upon the wavelengths, these standing wave patterns but his waves were way more complicated because they're three-dimensional, not just two-dimensional. All right? Now, that's nice and easy. That's just like 4, 1 through 7 energy levels. Unfortunately, with his quantum numbers, we have some sublevels. So the next one is called the azimuthal quantum number. Now, I didn't learn about this one in college. I learned about the name, but it's just azimuthal quantum number. But when I moved here from Baton Rouge, a little side note, I honestly believe that after LSU got shellacked by Auburn, the players purposely went out to find someone with COVID so they could get infected so they wouldn't have to play Alabama. And so they've gone from being so good to so bad. But anyway, when we moved here, we moved to Chelsea, and that was in 2001. And in 2001, Chelsea was just kind of starting, to get populated. Charter Spectrum hadn't made it out there yet, so we had no, we couldn't do internet or whatever. We had to have a satellite dish for TV. So one day my satellite goes out, and I'm trying to figure out, what's going on, what's happening, is my, not pointed in the right way. So I started looking at all the settings, and I find this azimuthal coordinate on my settings for my satellite dish. And I said, that's crazy. I've heard that number. I thought that was a chemistry number. Now, again, 2001 in Chelsea, we had dial-up internet. You guys remember, have you even heard about that, where it makes the funny noises as the internet's dial? It was the very beginning of the internet. Super slow. I didn't do any of that. I went to my 1963 World Book encyclopedias that I had at my house, okay? And I actually looked up azimuthal. And it says that it's a three-dimensional coordinate system that explains where in space an object is. Like a satellite out in space has to have a three dimensions, a X, Y, and Z, because we're in a three-dimensional sphere around the Earth. Okay? So it kind of gives that where in space is the electron going to be. That's what the azimuthal quantum number is going to tell us. Based upon its energy, the electron is going to be in different places, different patterns in space. Okay? So it states which energy sublevel the electron is in. Okay? Now there are going to be 4 main sublevels. The value of the azimuthal quantum number, oh, and by the way, we use N to represent this one. We're going to use L to represent this one. A script L. So, it can only equal from 0 up to n minus 1. Once again, what does the word quantum mean?
Atomic level?
No, it deals with atomic level stuff, but if you have a quantity of apples, what does that mean? A certain amount of them, right? quantum means specific amount. So our word quantity comes from the Latin word quantum. So this quantum theory says that the electron can only have specific amounts of energy. That's what Bohr said. It can only be on the first, it can only be on the second, it can only be on the third, it can't be anywhere in between. Schrodinger just took it a little bit farther with all of his math, which I don't understand, we're just accepting that it's true. That there's these variables that L limits the energy, it can only have these specific values, and this is the only way that we can describe the observations that we see with those line spectrum. So, this is a continuation under number 2 here. If n equals 1, what's the only possible value for L? 0. L can only equal 0. There's only one possible orientation in space when n equals 1 and L equals 0. If L equals 0, only one orientation. L equals 0 corresponds to what we call an S orbital. And I'll explain where these letters come from after I do all 4 of them. Okay? When anytime L equals 0 is going to correspond to an S orbital. Now, again, we have to say then what the heck's an orbital? Okay? That would be an orbit. That's what Bohr said, that the electron was in, actually Rutherford is the one that said the electron's in an orbit like the Earth around the sun. An orbital is the most probable place to find an electron. We can no longer say that the electron is in this set path. There's a thing called, I'm just throwing all kinds of stuff out here. The Heisenberg uncertainty principle. Now notice on this one I'm going to say PLE because that's talking about an idea. Anybody ever heard of the Heisenberg uncertainty principle? No. Anybody watch Breaking Bad? None of y'all have seen Breaking Bad?
No.
I watched a few.
I watched a few episodes.
Well, even in the beginning, Walter White, who's the chemistry teacher, has cancer. He needs money to pay for the cancer treatments and everything, so he starts selling drugs, starts selling meth. Okay? So he gets involved with drug dealers.
I'm gonna watch this show.
It's pretty dark. I don't recommend it, but I just thought it was so popular that most of y'all would have seen it. But I guess it was popular when you guys were too. They were too young to watch it when it was popular.
Yeah.
We were only 6.
So anyway, he becomes this kind of like drug lord guy in it, and his drug name is Heisenberg. Okay, and nobody knows what Heisenberg, but it's based on this Heisenberg uncertainty principle. Now, what Heisenberg won a Nobel Prize for was figuring out mathematically that you cannot know the exact position or speed, momentum, but the speed, the energy of an electron at the same time. The more you know of one, the less you know of the other. Okay? So, cannot know. I told you we're going to go deep today.
That's it. Yeah.
Cannot know the position and energy
I like the feeling it's better.
Y'all feel like
of a moving
you missed
particle.
a class somewhere in
I
between.
missed a whole year.
Yeah, this is what this feels. Sometimes, like, when we start learning new stuff, it's like, did I miss a class somewhere? Like, what led up to this?
Now we're getting, this is going to get very practical here as soon as I get through it all, which I may not even get through today. Okay? You cannot know the position and energy of a moving particle at the same time. The more you know of one, the less you know the other. Now, again, we take my 100-mile-an-hour tennis serve down the tee, bam. The uncertainty of where it is and the speed is so small that it's insignificant So when we're looking at it on a video, we can pretty much know how fast it's going and where it is at any given time. But when you get down to the size of an electron, traveling at the speed of an electron, the uncertainty becomes very great. So we no longer say that the electron is in an orbit. Now we're just going to give a most probable place where it might be. And I'm going to explain that a little bit more fully as time goes on. Okay? So, these orbitals have different shapes. Based upon the energy, the orientation in space is going to be a little bit different according to this azimuthal quantum number. So whenever L equals 0, it's going to be this S orbital, which is going to be spherically shaped. We'll go spherically shaped. Okay? In a sphere, there's only one orientation in space for a sphere. Now, if n equals 2, what can L equal?
1.
0 up to n minus 1. Which means L can equal 0 or L can equal 1. Two possible answers. Which means on the second energy level, we're actually going to have two sublevels. Well, L equals 0 is going to correspond to another S. But on the second energy level, that S is going to be bigger than the other S.
I hate math and chemistry math. They're so confusing.
You'll love it eventually, maybe.
You're going to get it. Trust me, it's okay to be confused right now, but I promise you, you're going to get it.
This is a high school class, right?
I know.
Didn't sound-
Okay?
I just want learning quantum
Hey.
physics and all that.
This is what the orbital of a 1s would look like, a little small sphere. So what that means is that when the electron has the energy corresponding to n equals 1 and L equals 0, when you plug it in these equations, the math says that the electron is going to be somewhere in this space. How it's traveling in there, we don't really know. We just know there's a 90% probability the electron is in that space.
What about the other 10%?
The other 10% it can be somewhere else, and I'll show you diagrams of that in a second, or tomorrow. This would be a 2s, still a sphere, but a bigger sphere. You guys seen those Russian dolls where you open them up and the smaller one is identical on the inside, and you open up, the smaller one is identical on the inside? That's what this is. You have to put this sphere inside of this one. The nucleus is in the center here. So you're going to have the nucleus and then this one surrounding it. And so we're going to have, here's the nucleus, you're going to have the 1s, and then you're going to have a bigger sphere right here. Because again, there's only certain distances from the nucleus that the standing wave pattern can form. So this would be my 1s, this is going to be my 2s, and the 2 being the n. Alright, stay with me. This area in between, remember in the standing wave, what did we call the area that didn't move at all?
Constant. Constant?
No?
What's the first one?
N.
Null for?
Well, what'd you call it?
Null?
Not null, but not null. It was a node, a nodal region. Okay. This is an area of low probability, an area where there's the destructive interference. The space in between here is that nodal region, a place where there's going to be a low probability of finding an electron. Okay? So we have the 2s. But now, when L equals 1, that corresponds to what we call a p orbital. Okay? A p orbital. Now, p orbitals are dumbbell shaped. A p orbital looks like this. Dumbbell shaped. Really just looks like an 8 on the side. But the greatest electron density is out here on the end. So a dumbbell, you know, it's got a little bar and then it's got the big round weights on each side. Okay, it's kind of what the P looks like, but it's very directional. Now the next quantum number is going to tell us why, but there are 3 different orientations in space for a p orbital. It can be on, this is what we call the px. You can have the py, okay? This is the y. And you can have the z in and out of the board. 3 different orientations.
Wait, hold on, so this, what do you mean in and out?
Like coming in and out of the board. Okay? 1, 2, and 3. So what we have, I gotta go in front, so you can see it. What we have is this, this, and this. These are your p orbitals. Notice you have x, y, and z axis. Hey, Caroline, just move the camera this way just a bit. Okay, so you have your x, y, and z. So you have 3 different orientations. Now, this is an orbital, this is an orbital, this is an orbital. This is the most probable place. When you give an electron a certain amount of energy, its wave pattern is going to be such that it's going to be in this space. Okay? Schroeder just figured that out. I don't know how. He's way smarter than me. Okay? Now, when? So, but the key is on the first energy level, you only have 1 value of L, so you only have 1 sublevel. On the second energy level, we have 2 values of L, we have 2 sublevels. L equals 0 always corresponds to an S, L equals 1 always corresponds to a P. Then, if N equals 3, what can L equal?
0, 1, or 2.
0, 1, or 2. So we have 3 possible sublevels. Nope. 3 sublevels. So N equals 0, L equals 0 is the S. L equals 1 is the P. And now L equals 2 corresponds to a D. All right. So, a D. A D orbital, we say, is rose petal shaped.
See, 4 and 12.
There's 1. And there are going to be 5 different orientations in space for this one. It can look like that. It can look like this. It can look like this. Okay? Notice that this fits right into here. These all kind of fit in between here, like that. And then one looks like a donut, a p orbital with a donut around it. Okay? Each one of these, this is one orbital, this is one orbital, this is one orbital, this is one orbital, this is one orbital. But when it's a d orbital, it has these kind of crazy shapes. But there's 5 different orientations, 5 different places around the nucleus, ways it can orient itself. Okay? A D. There's 5 of them. Then lastly, if n equals 4, what can L equal?
0, 2,
1, 2, 3. So you guys are figuring out the practical. So that means we have 4 sublevels. So each energy level has another sublevel. Now what would be a good name for L equals 3?
B.
L equals 3 is an F.
Right.
Okay? Now those are super complicated. I don't have models for those. They have like 8 lobes on them. They're pretty complicated shape. Now, where do these letters come from?
Greek.
Okay? when a spectroscopist, okay, a spectroscopist, okay, that's not an upset scientist. That is somebody who studies spectrum, okay, light spectrum, like a spectroscopist, okay? When they look at these, when we look at these, we say, ooh, look at the pretty colors. When they look at them, they can see differences. And so they can label the lines as sharp, principal, diffuse, or fundamental. Sharp, principal, diffuse, fundamental. That's what the SPDF. So when an electron is transferring, or going from a higher to a lower, when it's going from an S to a P, it's going to give one characteristic of a line. When it's going from a D to an S, it's going to give a different characteristic. So depending upon which orbital it's coming from, you're going to get different characteristics of your lines.
What do the letters mean again?
S stands for sharp. Okay, this is really good. That would be a trivia question for you. So that's more oh my information. Sharp. P stands for principal.
L-E or A-L?
AL. Sharp, principal, diffuse, D-I-F-F-U-S-E, and fundamental. But it's all based upon light. That's the whole thing. We're learning all about electrons by the light, the type of light that it's giving off. And all of these lines weren't the same, and so they're able to kind of say that there's sub-levels with it.
I'm slightly remembering the SPDF from 8th grade.
Okay? Well, we're getting there. All right, now, the reality is, listen, that when n equals 5, L can equal 0, 1, 2, 3, and 4. Now the 4 is going to be another sublevel. But the reality is that when the electron has enough energy to get to that sublevel, it actually can just escape from the nucleus. And so it's kind of like in Beauty and the Beast, and you got to tell me you've at least seen that one. Okay? In Beauty and the Beast, okay, there's that forbidden east wing or west wing or the forbidden wing. Okay, that's kind of the way it is in this hotel orbital, you know, that we're dealing with here as far as where the electrons are all going to be going. All right, so that's your L, your azimuthal, your sublevels. We have a G, H, and I theoretical, but we never use them. We only use these for SPD and F. After F, because they're theoretical, we just go alphabetical, G, H, and I. But because there's no lines that correspond to them to describe, because they really, mathematically they're possible, but the reality is they don't exist. All right, we only got a few minutes left, but let's make every minute count. The next one, the third quantum number, is the magnetic quantum number. And we use M sub L. And it can only equal minus L to plus L. So, when L equals 0, what's the only possible value of M sub L? 0. One answer, it doesn't matter that it's 0, means that we only have one sublevel possible. One orientation in space. Well, let me say one orbital, not sublevel, one orbital. Only one orientation. A sphere can only be oriented one way. When L equals 1, what can M sub L equal? Negative 1, 0, and 1. How many answers is that? 3. 3 answers means on the P sublevel there are 3 orbitals. I've already showed you that. It's the PX, the PY, and the PZ. Okay, Caroline, you need to move that camera back this way. I'm sorry. Okay? 3 answers, 3 orbitals. That's how I know that we have 3 different P orbitals on the P sublevel. When L equals 2, corresponding to a D, what can M sub L equal?
-2, 2, or -1, 0, 1,
Okay, so how many answers is that? So how many orbitals are there on the d sublevel? 5. You see a trend here. So when L equals 3, okay, this is your P, this is your D, this is your F, this one is your S. Okay, what's my M sub L going to equal? And L equals 3.
-3, -2, -1, 0, 2, 3.
7 answers equals 7 orbitals. So on the F sublevel, there are 7 different orientations in space, all equal energy, 7 ways in which it can be. So it's a pretty complicated thing,
Yep.
okay? We're almost done. There's only 4, and the 4th one's easy.
Yeah.
Like, easy.
No, it's either +1/2 or -1/2. We'll talk about that tomorrow. So if I want to do this, what we're looking at is the hotel orbital. It's a lovely place. It's a very lovely place. Okay? You put the positive here. So we want to say, where are the electrons going to be? Well, we can have them in an s orbital on the first energy level. On the second energy level, you can have an s orbital, but you can also have p orbital. You got 3 of them. So when I'm looking, I'm going to have electrons, so it's going to look like the electron is everywhere all at once, but the reality is very subdivided on where it can go. Now when I go to the third energy level, when n equals 3, I erased it, but you guys still have it. When n equals 3, L can equal 0, 1, and 2, which means I have another s orbital. Okay, I have more p orbitals. They're going to be the same shape, just bigger. The Russian doll thing. Then I'm somehow going to have to superimpose those 5 d orbitals. Now that's beyond my artistic abilities. Okay, and so, but again, the whole point is this: the electron's energy is quantized. They can only have specific amounts of energy. So when we put all this into the equation to describe the energy.
Period at this time.
When you describe the energy, it can only be in certain places around the nucleus. It can't just be anywhere it wants to be. It looks like this cloud. It looks like a fan. It looks like the fan's everywhere all at once. But the reality is, it's in a very specified place. Tomorrow, this will make more sense.